Hello and welcome to this discussion on optimizing the product layout. So product layout is basically a high volume system. Why? Because it produces large quantities of low variety, right? So that is a product layout, that is a characteristic trait of a product layout. And any high volume system in general have this characteristic of using standard equipments performing activities on identical or highly similar products. And this can be extended to the service sector when the products are nothing but the customers who are flowing through the system. And the main challenge in designing a high volume system is the challenge of achieving a smooth rate of flow. And this problem is referred to as the line balancing problem. So line balancing is the process by which I am going to assign these activities to enclosed spaces called workstations such that when products flow through them, they have a smooth rate of flow. What do I mean by this? Say, I have two workstations, workstation 1 and workstation 2. When item A1 enters workstation 1, right, it is empty. Item workstation 1 is empty. And when item A1 exits workstation 1, item A2 is ready to enter workstation 1, right? So as the items flow through this without any gap, the next item comes in. So there is a smooth rate of flow. There is no queuing before or after the line. So item A1 has exited, it is ready to enter item is ready to enter workstation 2 and workstation is ready to accept it. And when item A1 is exiting workstation 2, item A2 is ready to enter workstation 1. So there is a smooth rate of flow between the items that are flowing through the high volume system. And this is the problem that we are looking at when we are looking at the line balancing problem. How to ensure that activities are grouped in the workstation such that the time in each workstation is almost same. When we are looking at a line balancing problem, the first thing to determine is what should be the time in any given workstation, right? So that time is referred to as the cycle time. So the cycle time is the maximum time that I allow for any item to spend in a given workstation. At the end of that time, it leaves that workstation, moves to the next workstation where it again stays for the same amount of time, the same cycle time. So across different workstations, the cycle time is the same. Let's look at this through the eyes of an example. Say we have 5 activities. Windshield fitting, which takes 2 minutes. Then we have the wiper fitting, which takes 8 minutes. Then we have the door fitting, which takes 2 minutes. Then we have the window glass fitting, which takes 5 minutes. And finally, the sun film pasting for all the glasses, which takes 3 minutes. So these are the 5 activities. So given a set of 5 activities, what should be my cycle time is the question. So this cycle time can be between two values. The first is the minimum cycle time. Say I perform these 5 activities in 5 separate workstations. Then in each workstation, the time that it spends would be the activity time. However, I should achieve a smooth rate of flow. So what would happen? I would be basically doing activity in the first workstation for 2 minutes, but the item will not come out in 2 minutes because the second workstation requires 8 minutes. So the item will spend 8 minutes in workstation 1. In 2 minutes, the activity is completed, but it will still be there. And when it leaves, it is ready for workstation 2 without any waiting. So the conveyor will move in such a way, or the item will move in such a way, or there will be spaces for enjoyment if it's a service sector, so that by the time the windshield is fitted and you are allowed to move to the next workstation is empty. So if I have to do this, the cycle time, the minimum possible that I will be able to achieve is when I do wiper fitting, is the time that I take to do wiper fitting, which is 8 minutes. So the minimum cycle time is the longest activity time amongst all the activities that is present to me. So that was 8 minutes per unit per workstation. And the maximum cycle time that I can achieve is when I do all the activities put together in one station. Then for doing windshield fitting I need 2 minutes. For doing wiper fitting I need 8 minutes. For doing door fitting I need another 2 minutes. For glass fitting I need 5 minutes. And finally sun film pasting I need 3 minutes. So 2 plus 8 plus 2 plus 5 plus 3 is the total time that I require to complete all the activities if all of them are assigned to a single workstation. So that would be 20 minutes. So given a set of activities, the minimum cycle time that is possible and the maximum cycle time that are possible can be determined. And once you have determined the minimum and maximum cycle time, then you can determine what is the minimum and maximum output rates that are possible. So the maximum output rate that is possible is basically the total working hours that is available, the total time that is available divided by the time per station, which is the cycle time. So let's say I am going to work for one 8-hour shift a day, and I'm going to produce, and every hour in that shift is going to have 60 minutes of working. So 60 into 8, which is 480 minutes per shift per day, and divided by 8 minutes per unit. So I'm going to basically be producing 60 units every day. So that would be my maximum output that I can achieve. But if I group all of them and do them in a single workstation, then 480 divided by 20, which is going to be 24 units per day. So my output rate will fall between 60 and 24. And this is applicable only when I do not have parallel lines. For our discussion, we will be limiting our scopes to only non-parallel lines. We are going to do all the activities on one line. There is not going to be any parallel lines that are doing similar activities. Alright. So, the cycle time is usually determined based on our desired output rate. So, if I want to achieve a certain output rate and I have certain amount of time, then what is the cycle time that I want to target? So, that would be the problem. For example, let's say I want to achieve 80 units per day as my output. Then the cycle time is going to be the total time that I have, which is 480, divided by 80 units per day, which is going to be 6 minutes per unit. But the question is, I want 80 units per day. Is it feasible? The feasibility is basically determined by whether the cycle time fits in the range of minimum and maximum, which is 8 and 20 minutes. Since it does not fit between 8 and 20 minutes, I can say that the maximum output rate that you can achieve is only going to be 60 units per day. Why is this important? Let's say I want to do an output rate of which is 30 units. Then appropriately I can determine what is my cycle time and create my groupings. Here I want to have the maximum output, and the maximum output is only possible for 60 units per day, and to achieve 60 units per day I need at least 8 minutes per unit, which is my cycle time. Alright, so once we have determined the cycle time, we have to see how many workstations are required to get that cycle time of 8 minutes. So that is going to be the next question. How do we determine the number of workstations? And this is determined as the theoretical minimum number of workstations, which is n-min, as the total activity time, which is 20 minutes for the 5 activities, divided by the cycle time, which is going to be 8 minutes per unit. So I need 2.5 stations. But the term says theoretical minimum. So in theory I need 2.5, but practically 0.5 station is not possible. So I need to round it up to 3 stations. So the minimum number of workstations that I need is 3. I have given you an explanation for why it is called the theoretical minimum. Theoretical, the term theoretical in that theoretical minimum. I have to say why it is minimum. The minimum comes because I need 3 or more, and the more would come into picture based on how efficiently I can group the tasks. And the efficiency of grouping tasks is basically determined by the precedence of the task, the tasks that have to be completed before a current activity is performed. To give a perspective, let's say I do those 5 activities, but before doing wiper fittings, the windshield has to be fit. Before I can do glass fittings, the door and the wiper have to be fit. So then before I do the sun film pasting, all the other activities have to be completed. So only if these are done, I would be able to do it, I would be able to produce a product that is usable. If it is done in some other way, it is not practically feasible. So that is why the term theoretical minimum comes into picture. Minimum I need 3. In our case, you would be able to see that I can do it in 3, but in some scenarios, the 3 may not be sufficient, we will have to go for more. So for this case, we are able to do it in 3 workstations. The first workstation, we will be doing the windshield fitting and the door fitting, which accounts to 4 minutes out of the 8-minute cycle time. Then in the second workstation, I will do wiper fitting, which takes the complete 8 minutes. And in the third workstation, I will do window glass fitting and the sun film pasting, which takes around 8 minutes. Right? So in 3 workstations, I have completed my activities. Right? So this is a grouping that meets my precedence that I have got in 3 workstations. How efficient is this? So that is where the concept of balance delay comes. So balance delay, or the percentage of ideal time, is basically going to tell you how much idle time as compared to your total time is present in the system. And please note, the balance delay and the efficiency of the line, both of them are expressed only in percentages. They are not expressed in decimals. So if I have to compute the balance delay, what I would do is, for any given workstation, so for workstation 1, I would compute the ideal time as the cycle time minus the activity time, which is going to be 8 minus 4, total activity time, which is 4. Similarly, for workstation 2, it's going to be 8 minus 8. Similarly, for workstation 3, it is going to be 8 minus 8. So the total of this is going to be 4. And the balance delay is going to be 4 by 8 into 3. Since I am using 3 workstations, 3, and 8 minutes per station is the cycle time. So 4 by 8 into 3, which is going to be around 16.7%. So this is going to be my balance delay. So if I have so much amount of balance delay, the efficiency of the line is going to be 100 minus 16.7, which is going to be 83.3%. Right? So I have designed a line which is efficient for 83.3%. And this is the best efficiency that is possible. I cannot improve my efficiency without violating my precedence. Alright? So this is the manual method of solving a line balancing problem. But we have given the title to the discussion as optimizing a product layout. So why is optimizing coming into the picture? For a small number of activities, this manual method would work. But let's say you are given 50 activities, 100 activities, a very complex network diagram. How will you do it? You need a mathematical model to solve the problem. And that mathematical model, the optimization model that I'm going to be talking to you about, is called the assembly line balancing model. Since I'm going to talk to you about the assembly line. And so it's called the assembly line balancing model. And for this optimization model, the first thing that I'm going to present to you are the parameters and the decision variables. So in any optimization model, there are 3 things that would be required. The first one are the decision variables, the second is the objective function, and the third is the constraint. So in this, I'm going to first talk to you about the decision variables. The parameters basically refers to your inputs. So say that you are given a set of activities which is A, and there are n activities that are there. And these n activities have to be assigned to workstations such that there are m workstations. And the activity time for each of these n activities are given by TA. And the precedence for an activity is given by the set PA, right? And finally, what is the cycle time at any given workstation? So these are all the inputs, and they are called the parameters for your model. Alright? Right. So what is the decision variable? I basically want to know whether an activity is assigned to a workstation. So is an activity A assigned to a workstation W? If so, it is 1, else it is 0. So that is our decision variable. It's a binary. Yes, it is assigned. No, it is not assigned. Right? So that is going to be our decision variable. A second decision variable for us is if an activity is assigned to a workstation, then it is 1. If not, it is 0. So the second decision variable for us is whether a workstation is used or not. I have m workstations. Out of these m, which are the workstations that are used? So that is the second question. So for that we have a decision variable, whether a workstation is used or not. So these are the parameters and decision variables for a model. Then let's look at the next two pieces, which is the objective function and the constraints. So first the objective function, and here we will look at the verbal forms of the objectives and the constraints first. So what is my objective? I want to achieve an efficient line. So I want to achieve a line where I have minimum number of workstations. Why? Because as I increase my workstations, as I increase the number of workstations, let's say I put a fourth workstation and do sun film pasting in that, then what will happen? The third workstation will have a activity time of 5 and the fourth workstation will have an activity time of 3. So my total will now become 4. My balance delay, basically, my balance delay would now become, if I use 4 workstation, it will be 4 plus 0 plus 3 plus 5 divided by 4 into 8, which is obviously going to increase, right? So my balance delay, the total amount of ideal time that I spend, is going to increase. So to avoid this, I want to minimize the number of workstations that I use for assigning all of these activities. So that is going to be my objective. And I am going to solve this objective with a constraint that the cycle time in any given workstation must not exceed my cycle time. So the total activity time that I assign for a workstation must not exceed my cycle time. So that is the first constraint, cycle time constraint. The second one is the assignment constraint. So each activity must be assigned to some workstation. I can't say, okay, I will not assign an activity to any workstation. It must be assigned to a workstation. So that is the assignment constraint. The third is the precedence constraint, which basically means the activities when I assign to workstations must follow a precedence, must follow the precedence that is provided to you. So that is the third constraint. Finally, all my decision variables and must be non-negative. In our case, they are going to be binary in nature. So the non-negativity constraint. So these are the objectives and the constraints. So now we will look at how to formulate these objectives and constraints using the decision variables from the previous slides to the mathematical form. So in the mathematical form, we want to minimize the number of workstations. So what does that basically translate to? So I have a variable, I have, let's say, 3 workstations, 1, 2, 3, and the variable y, w, where w is going to be 1, 2, 3, can either be 1 or 0 for each of these workstations, right? So I want to minimize yw. So what I should do? I should basically sum up y1 plus y2 plus y3, and I want to minimize this. So when I minimize, I can either get a minimum value of 1 or a maximum value of 3. So I can have at least, I should have at least 1, since all my activities have to be going into one of those workstations. So I can have 1, or I can use all 3 and get 1 plus 1 plus 1, which is 3. So this is my mathematical notation. So in terms of, summations, if I have to represent it, I would sum it up, w is equal to 1 to m, y, w. So I will have 3 workstations in the previous thing we saw. So y1 would be, so y when w is equal to 1, y when w is equal to 2, y when w is equal to 3, sum up all of these 3 and minimize it. That is going to be my objective. So sum up y, w, where w goes from 1 to m, and minimize that. So that is the mathematical notation of the objective. So next we look at the constraints. And what is our first constraint? Our first constraint says that if activity is allocated to the workstation, then the sum of all those activity times must be less than my cycle time. So let's say I take a workstation 1 and I have 3 activities, activities A, B and C. So if XA is assigned to workstation 1, it is 1. If XB is assigned to workstation 1, then it is 1. If XC is assigned to workstation 1, it is 1. Then the sum of these times TA plus TB plus TC must be less than or equal to my cycle time, which is going to be 8 minutes for my case, right? So we saw the same thing in the previous slides. We want to have maximum output, so we are telling a cycle time of 8, so it must be 8. And this 8 is applicable only if this workstation has the items allocated to it. So in mathematical notations, I am going to sum up all the activities that are assigned to this workstation. So if they are assigned, this is equal to 1, and when it is assigned, this will give me the time. If I sum this up, I will get the total time, activity time, that is being consumed by a workstation, and that must be less than my cycle time, which is 8 minutes, if that station is used, which is 1 or 0. So for every station that is used, this total activity time must be less than 8 minutes. So that is the first constraint. So the constraint that the cycle time must be met in mathematical notations. So summation over all my activities, basically my set A, time for an activity into XAW, whether it is assigned or not, must be less than or equal to cycle time into whether the station is used or not. This is for all my W and element of capital W. So A is equal to 1 to N, and basically A is an element of E, right? So this is going to be your mathematical form. The same thing is going to be a mathematical form for your first constraint. Your second constraint, which is the assignment constraint. So I must ensure that the activity is assigned to at least one station. So given that there are 3 stations, only in one of these 3 I must assign A, right? So X A for the first station plus X A for the second station plus X A for the third station must be equal to 1, which means at least one of them should be 1 and the others should be 0, because these variables can take a value of only 1 or 0, right? So only one of them can be 1, the others must be 0. So that is what it is. Across all my stations, only in one of them I can assign the activity, in the others it must be 0. So summation over W, XAW must be equal to 1 for all my activities. So that is the second constraint. The third is the precedence constraint, and this is where things get tricky. So I must ensure that, let's say I have activity A, and this does not have any precedence. No precedence. For activity B, I have activity A as precedence, and for activity C, I have both A and B as precedence. So the precedence diagram for such a scenario will look something like A, B, C, and then E. So this is my precedence diagram such that activity A has no activities that need to be completed before it. For doing B, I need to ensure that A is done. For doing C, I need to ensure that both A and B are done. So in such a scenario, how will I ensure that when activity C is assigned, A and B are completed? So in whatever station activity C is assigned, that is where it is going to be 1. If it has to be 1, then I must ensure that A is assigned in any station K such that K is less than W. So as an example, let's say I assign workstation, I assign C to workstation 3. Then XA1 plus XA2 plus XA3, it must be less than or equal to. So in one of these stations, A should have already been assigned. Then only I can assign C to workstation 3. Similarly, since both A and B are predecessors for C, I must also ensure that XC3 is less than or equal to XB1 plus XB2 plus XB3. So for B, if I have to write, so if I have to have B in station number 2, for example, it must be less than or equal to XA1 plus XA2. or if B has to be assigned in 3, then the predecessor A should have been done either in 1, 2 or 3. So this is my precedence information. So in mathematical notations, it will look like any given activity A, if it has to be assigned to activity W, then for all preceding activities, it must be assigned to a workstation that is less than or equal to W. So this is the mathematical notation of our precedence equation. So for any activity that is a presiding activity for P, for A, it must have already been completed in a workstation that is W or lesser than W before it, and the activity, the task A, is assigned to a workstation that is in W or later, right? So that is what is basically established here. So this is the precedence equation. Finally, we have the non-negativity, where all the decision variables must be binary. They should be either 0 or 1. So that is our final non-negativity constraint. Since you have already gone through courses of machine learning where you have done extensive Python coding, what we are going to do in this course for particularly this problem is we are going to give you the optimization model coded in Python. Please run it for the datasets that is provided to you. The code is self-explanatory. In case if you have any doubts, please post it in the discourse or ask them during the live sessions, and we will be happy to answer any of your queries. I would like to conclude by saying, for those people who have exposure to operations theory and they would be thinking, come on, this problem is an NP hard problem. And NP hard basically means as the number of XAW starts to increase, the time to solve the model drastically increases. So optimization is not a feasible method for solving large scale problems, and we will use some other techniques called heuristic methods. Even for those heuristic methods, you need to know how to mathematically code. So the mathematical formulation forms the fundamental for them. And heuristic techniques are beyond the scope for us, so we will not be discussing those in this particular level. So with this, we conclude our discussion on facility layouts. Please go through the contents once more to be more clear. Do run the Python code, get the output, and see whether they match with whatever we have discussed so far. Thank you.